good rates for you. You're in the front row. Thank you. I'd like to start by thanking the organizers for the invitation to Bonn. So what I talk about today is a kind of reduction process in symplectic geometry. And the general idea is to produce a holomorphic symplectic manifold of smaller dimension than the one you start with. And then to somehow use that in novel ways, possibly to say something about the space you started with. So I probably don't need to define holomorphic symplectic geometry, but let me start anyway with just in case you've been asleep for the past 2 days. A holomorphic symplectic manifold will be a compact Kähler manifold of even dimension 2n with a non-degenerate holomorphic two-form sigma. And here non-degeneracy means that the sigma induces an isomorphism between tangent and cotangent bundles, or equivalently, the top power of this trivializes the canonical bundle. Okay, and I also just want to point out that holomorphic will imply that actually the form is closed, is declosed in this case. Okay, so this is just from Hodge theory. I mean, it's D bar closed, but then actually it's closed for the D as well. Okay. And also we say that this is irreducible if it's simply connected and it's not a product of two. What does that mean? So it's not a product of two things of lower dimension. Okay, so that's the basic setup. And so now what I want to look at is if I take inside here some complex submanifold, or to begin with, let's say we take a complex hypersurface. So then if you restrict the two form to that hypersurface, so in general, well, it's not going to be non-degenerate anymore. So the rank is going to drop. And what you find is that the rank is going to be 2n minus 2, at least on the smooth part of y. Okay. And so you can look at the directions in y in which this thing is becoming degenerate. Okay. And that gives a distribution and, in fact, a foliation on y. So we define f to be the kernel of y. And you can think of this as giving a map from the tangent bundle of y to the cotangent bundle. So the kernel is like a subsheaf of ty, or distribution. And so this defines, because of the rank is 2n minus 2, so this defines a rank 1 foliation at least on the smooth part of y. Okay, and this is called the characteristic foliation. Okay, so this is for a hypersurface. You can do something similar for higher codimension submanifolds as well. If the codimension of y is bigger than 1, then you still get a foliation on the smooth part of y. And this is because it's the kernel of a closed form. Okay, so I mean, this is just going to define your distribution inside here, and then, but it's going to be closed under brackets because the form used to define that is closed. Okay. Yeah. So that's a. So this is not going to be. So however. In general, the rank of this, even on the smooth part of y, as defined, may not be constant. Okay, so you get a foliation that may not be regular anymore. So actually, a special case, though, is when... So a special case in this higher codimension situation is if what we call coisotropic. So it's coisotropic if the rank of sigma restricted to y. Let's assume this is a smooth now. So then its rank should be equal to 2n minus the codimension of y. Okay, so x is 2n dimensional here. So if it's equal to that at all points. And so this is the same as saying that the rank of the foliation is equal to the codimension of y at all points. So this is the minimal rank that this could be at any point. If you have something of codimension, well, if it's codimension y, then the smallest rank you can have for this would be this value, and you want it to be equal to that at all points. Okay. So more generally, what you would have is the rank would be, or you would have a sort of stratification by subsets where this has different ranks, and it could. I think it'll drop down. The rank could drop down on closed subsets. Right? So if it's equal, if it's equal to this at a generic point, then it should be equal to this everywhere. Okay, so an example of this would be if there's a group action on. So suppose X admits a Hamiltonian group action. Of complex reductive group. So for example, like a C star action. Well, I guess maybe I don't want. I mean, let's allow this to be non-compact as well. Okay, so then you have a holomorphic moment map. And then the sort of level sets of the moment map are going to give coisotropic submanifolds inside X. And so you choose lambda to be some value in the center of, or the joule of the center. And so then this will be coisotropic. And the leaves, so you get this characteristic foliation on here with it's going to be regular everywhere, and the leaves of the foliation are just the G orbits. And the space of leaves is the holomorphic symplectic reduction. So, so again, yeah, and you want to consider maybe a non-compact example. The simplest example would be the non-compact example where you have just the C star acting on a symplectic vector space, and then of course the level set for 0. The moment map would be the Z1 times W1 up to where these are just the coordinates on C2n, and so we could take the level set where this is 0. And then when you take this quotient, then you get cotangent bundle of Pn minus 1. So here, I mean, this is like a GIT quotient, so you're throwing out the stable. You're throwing away the unstable points. Okay. So the point here is that the space of leaves is then naturally a holomorphic symplectic structure. And that's something you would expect in general, because by sort of quotienting out by the leaves, you're sort of quotienting out by the directions in which the holomorphic two-form, sigma restricted to y, is degenerate. And so then it should descend to a non-degenerate two-form on the space of leaves. This is singular? Yeah, do I want to put lambda? Well, no, then lambda's then it's a smoothing of it. Yeah, so, okay, so then maybe I want to put lambda here, be non-zero. But then this is a smoothing of this. It's a singular. Well, anyway, you probably know this. Okay, so yeah, it would be singular. Okay. Anyway, so to come back to the general situation where you have a foliation rather than an actual group action, then in order to sort of get to this stage of constructing a space of leaves, well, first thing you need is that the leaves should be compact, so that you can construct that space. So firstly, you can ask when are the leaves, or let's say when are the leaves algebraic? Okay, so imagine we're back in the projective setting. So in this case, we say that f is integrable, it's algebraically integrable. Okay. And the main results here is Quebecus, Sola, Conde, and Thoma. So I mean, this result I'm about to say, of course, is sort of refinement of earlier results of Miyaka and Bogomolov and McQuillan. And but their statement is that if y is a normal and projective, and if f is a foliation on y, and C is a complete curve in the smooth locus of y, and in the regular locus of f. So as I said earlier, you have this stratification. So the regular locus is like the largest sort of risky open subset where you have a constant rank here. Eh? No, this is just a general statement. I'm not assuming we're in this earlier situation. Regular locus. Right, so then what you need is that if so we've got the curve. If the foliation restricted to C is ample, so if this is an ample vector bundle. So I mean, on the regular, if C is in the regular locus of F, then this is a vector bundle of C. So if this is an ample vector bundle, then the leaf through any point of C is algebraic, and the closure of a generic leaf through C is rationally connected. So in particular, if F is regular everywhere, then then this will imply that all the leaves are rationally connected. So I mean, this uses sort of bend and break arguments of Mori. So once you have this curve C, you show that you can that it deforms, and then eventually it breaks up, and then you get rational curves, and then you show that the rational curves, once you get the rational curves of the smallest degree, then they actually lie inside the leaves of this foliation, and that's how you get this rationally connectedness of the leaves. Okay, so I think McQuillan was here last week. Was he? McQuillan, did he speak here recently? I don't know. Maybe he talked about results like this already. Okay, so to come back now to the situation where we have y sitting inside the holomorphic symplectic manifold, So firstly, for a hypersurface, so the foliation here is the same as the determinant of Ty, because if you look at the quotient of Ty by F, at least this is over the smooth part. So this is going to be trivial because we have the holomorphic 2 form is sort of descending to something non-degenerate on here again. So the top power of this will be trivial. So this is a on the smooth part of Y, this is a line bundle now. It will be the isomorphic to this, and this is of course just the dual of the canonical bundle, which by adjunction on X, because X has trivial canonical bundle, is O minus Y restricted to Y. As Kx is trivial. Okay. So I mean this is what the foliation is going to look like in this case. So we want this to be ample on some curve. Okay. In order to apply this theorem up here, so we want O minus Y to be ample on some curve. On curve C in Y. And just to see what happens at the other extreme. So I mean, this would give you that the leaves are all rational. So I mean, particularly if Y is smooth, the leaves are just going to be all rational curves. But at the other extreme, if O Y is actually ample on X, then in particular be ample on any curve C. But we also have that KY is, well, this will be ample. So Y is of general type. Okay. And in this situation, Huang and Buick prove that the leaves are, or the generic leaf is not algebraic. So if Y is of general type, again we're in a situation here where it's sitting inside a holomorphic symplectic manifold. Then the generic leaf of F is not algebraic. Okay. So actually, this is for a smooth hypersurface Y. Yeah, if Y is a smooth hypersurface, and then you have the hypothesis of this theorem, then you have the leaves are all rationally connected, so they're just P1, they're just rational curves. Okay. Does that answer your question? Okay. Yeah, I think so. Yeah, the space of leaves. Yeah. Yeah. So at this other extreme, though, then you don't have any. Well, I mean, you could still have some algebraic leaves. The generic leaf is not algebraic, so you don't really have any hope of creating a quotient in this case. And I think also, at least I saw on the webpage that Kampanar spoke here last month, and he, I just read the abstract, but he said he had a related result saying that with Emmerich that, so here assuming general type, I think his result is that if Y is not uni-ruled, then again, you get the same conclusion. The generic leaf is not, of the characteristic foliation, is not algebraic. And I think his result applies when X is irreducible holomorphic symplectic. I think this one is you don't need irreducibility of X for their statement. Okay, so that's, so let's suppose now though that we get we have the algebraicity of the leaves, and the second question is to, what kind of space of leaves can you get? So is there a nice space of leaves? Well, so the answer is yes. So if all the leaves, even in a fairly general setting, if all leaves are compact, if you're in the sort of compact complex setting, if all the leaves are compact, then I mean the picture then is that you have let's say you have this leaf L, and it's a nearby neighborhood. So then Reeb's stability theorem implies that every leaf has a saturated neighborhood. So what this means is that there's some neighborhood of the leaf which is just a union of leaves as well. Okay. So then you can take a transversal slice here with our central leaf L hitting this at, say, 0. So let's call this V with 0 in there. And so then what happens is that pi, so I mean this is not quite a model for the space of leaves yet, because I mean this leaf here could sort of go around and come back on the other side. Okay? But what happens is that there's a map from the fundamental group of this central leaf, L, to the holomorphic automorphisms of this sort of transversal slice fixing 0. And it has some image in here which is known as the holonomy group. And then V mod HL is a local model for the space of leaves. And so the space of leaves is really given by sort of patching these little pieces together. So of course, in the sort of algebraic setting, there's probably a yeah, I'm okay. Okay. Yeah. I mean, these are good questions. I'm not entirely sure how to answer them. Perhaps in this generality, I'm not quite sure how to answer that. But in the situations we're looking at, if we can invoke this theorem, then we have rational connectedness. So we have simply connectedness of the leaves. So then all of this holonomy group just disappears. So I'm not quite sure how to answer it in the full generality, but it doesn't really matter for what we're looking at. So for rationally connected leaves, we have that the pi 1 of the leaf is trivial. So the holonomy group is trivial. And so in fact then in this case then the space of leaves is smooth. Okay. If your leaves are all rationally connected. And moreover, this holomorphic two form descends to the space of leaves. So I mean, here you would say if there's another sort of local model, then you get a map from. You can identify these local models, and the identification turns out to be to preserve. Well, you can identify them in such a way that you preserve the holomorphic two forms. So you end up with a holomorphic two form on the space of leaves. Sorry? This is smooth?
Yeah, no, what is the function and why?
Oh, so do we need y? Well, yeah, at least. if y is smooth. Otherwise, you would be looking at the smooth locus. Yeah. Perhaps just assume y is smooth for this thing. Okay, so some examples then. All right, so probably the simplest kind of example is to look at the case when you have y equal to the exceptional locus in the Hilbert scheme of 2 points on a K3. And then, of course, this maps down to the diagonal down in the symmetric product, which is a K3 isomorphic to a K3 surface, and the P1 bundle over that. So in this case, these P1s are the leaves of the characteristic foliation on Y, and this is your space of leaves. And notice here that Q, the Baville-Bogomolov form of E is minus 8. It's a square minus 8. And there's a theorem of Buxum, and I think, well, there was a partial result by Daniel on, which was a partial statement, which was proved earlier by Daniel. So if Y is an irreducible hypersurface in X, whose square is negative with respect to the Bogomolov form, then Y is uni-ruled. Okay. So this theorem, I mean, you can get this very easily in the case when Y is smooth from this foliation point of view. I mean, his theorem applies more generally when Y could be singular as well. But let's just see, like when if Y is smooth, so if Y were ample or Neff, if it's Neff, it's going to be limit of ample things. Then we would have the Baville-Bogomolov square would be positive, or at least non-negative. So since that's not the case, it can't be Neff. So therefore, there's some curve with on which Y is negative. Right? And so then that's the hypothesis that we need up here. So O minus Y C is positive. So I mean, this is saying that remember this is F. Right? So the characteristic foliation is ample on this curve. And so then applying this theorem up here. So all the leaves are P1s, and then Y is uni-ruled over the space of leaves. when y is ample and uniruled. I mean, what happens with the foliation?
Yeah.
Well, I think can that happen? Can it be ample and uniruled? I mean, maybe, I don't know, the uniruling is not in the direction of the foliation then, perhaps?
So if y is ample, then you
It's,
y, all y is ample, then y is
I mean, I don't know if it could still be uniruled, but I mean, this is saying that the leaves are not going to be algebraic. So if there is a ruling, it's not going to be in the direction of the foliation. But oh, can it be uniruled? Okay, yeah, yeah. Well, okay. Yeah. So another example is if X is a Mukai moduli space of MV or stable sheaves on a K3 with Mukai vector given by V, and let's assume that for the generic guy, the generic sheafy has no sections. Right? Okay, and then let Y be. So this could be a hypersurface, or it could be higher codimension. Let Y be the Brill-Noether loci, where where E actually has sections, right? And also let's assume here that H, that generically in Y we have a single section. I mean, what I'm about to say can be modified when this is larger. Okay. So then we have a short exact sequence, and we get some sort of coconal of the section. So I mean, let me just write down the Mukai vectors here. V prime equals. And so in this case, there's a rational map from Y to some other moduli space in V prime. It's by taking E to V F. So of course, I know you need to show stability of F and so forth. So I mean, this is something you need to check in specific examples and so on. And the fiber of this map, or what will actually turn out to be the leaf of the characteristic foliation, sitting above, say, F in here, is given by, well, it's just given by, how do we get extensions of F by O? So it's the projectivization of X1 F O. So you get some projective space. That's your leaf above F here. And so this will be the or birational to the space of leaves of this characteristic foliation. So often when you find examples, you can try to see whether they can be interpreted in this framework in terms of Brill-Noether loci in Mukai moduli spaces. So, okay, so now let me come to the sort of main point. So I want to sort of propose a fantastic idea for classifying holomorphic symplectic manifolds. And I'm using the word fantastic here in the sense of fantasy. So maybe I should really call fantastical idea. But at least have one example. Well, have a few examples where one can follow the following set of ideas. So the first step is to find a suitable submanifold y in X. For example, like this result, like an effective divisor whose square is negative. Of course, it's very difficult to find such things. And then secondly, show that that the characteristic foliation has rationally connected leaves, and that you get a nice space of leaves as a holomorphic symplectic manifold. And then 3, describe X in terms of this lower dimensional guy. So ideally in step 2, you get here a surface, so K3 or an abelian surface. And then you want to just try to describe X in terms of that K3 or abelian surface. Okay, so I guess in some sense, Gianluca's talk earlier is certainly related to this idea that you started with a fourfold of K32 type, and then showed that this ample class, there was some uni-ruled divisor in there, and then you can recover the K3, and then you show that thing is then deformation of that that hill 2 of that K3. So I want to describe an older result of Mukai, which is kind of on a similar. It uses a similar idea, but the divisors here are not ample. Rather, they're sort of more negative things. So it's really more like this example up here with the. Well, in fact, it turns out to be exactly this example up here with the exceptional locus of the Hilbert scheme. So his result says that if you have a projective, irreducible holomorphic symplectic manifold of dimension 4, and assume there's a birational morphism from X down to some lower thing, which is a divisorial contraction. And such that we have the following conditions, that this contraction on the level of when you restrict it to Y is just a equidimensional. Yes, thank you. 2 is that Y is 2 divisible in narrow subvariety of X. And 3 is that Y to the 4th is 192. So I mean, it can get fairly specific what you need, right? So then he says that then S is a K3, and X is the Hilbert scheme of 2 points on S. So this is kind of the example of what you want to do. And as you can see that you really need to get all the conditions just right to be able to get the conclusion you want. So I mean, so he doesn't use foliations in any way. In fact, I mean, his hypothesis really is that you already have this contraction where the hypersurface is contracted to a surface. I mean, one can maybe improve on this a little bit by saying that if X is of K3 type, so here I think we just need that it has the same cohomology ring as Hill 2 over K3, and then if Y is an irreducible divisor with square minus 8 and 2 divisible, subvariate of X. So then you get, well, I mean, this will tell you that Y to the 4th is 192. But more importantly, if you run the log minimal model program on X and epsilon Y, then, so there'll be some sequence of directed flips. But eventually what gets spat out at the end here is something where you have a divisorial contraction now, and you contract this guy Y prime. The generic fiber here is P1. So I guess Wiesbar's results said you either get P1 or two P1s like this. So here you need to use the two divisibility to show that this case of two rational curves like this doesn't happen here, that it's just a P1 bundle over this. So this is one way to sort of get the first part of the hypotheses from this statement. I guess, I mean, the hard part about doing anything like this, though, is that it's very difficult to get effective divisors whose square is negative with the Bogomolov form. He uses the fact that Y is two divisible to look at the double cover of X branched over Y, and then the corresponding double cover of Z. And then he shows that has to be holomorphic symplectic and a product of two K3s. And then he shows, in fact, that the K3s are both isomorphic to this single one S. Yeah, so it's difficult to find effective divisors with negative square. I mean, we know that like from the hypercale S by Z conjecture, if you have an isotropic divisor, it's very difficult even then to show that you have an effective divisor in that class. So what you really need is some. You need to be given some sort of geometric situation where you can find this divisor Y, or maybe some higher codimension submanifold Y with this sort of negative property that gives you this nice behavior of the characteristic foliation in space of leaves and so on. So I want to describe one example where we get this. This is where we look at Lagrangian fibrations by Jacobians. So let x over Pn be a Lagrangian fibration given by the compactified relative Jacobian of a family, or flat family of genus n curves. And here I want to assume that they are reduced, irreducible, and also Gorenstein curves of genus n, so arithmetic genus n over P. Pn. Okay, so in this situation, the expectation is that this is the Brill-Mukai system. So this family of curves is a complete linear system on a K3. Therefore, X is the Brill, what's known as the Brill-Mukai integrable system, which essentially means just this: you take a complete linear system of genus n curves on a K3 that'll move in a family parameterized by Pn, and then you take the compactified relative Jacobian of that family of curves, and that gives you what's known as a Brill-Mukai system. And in particular, this is a Mukai moduli space of sheaves on a K3 surface. So it's a deformation of Hilb n of the K3. Okay, so this was first investigated by Markuszewicz, and he showed that this is true for n equals 2. So you have a family of two-dimensional Jacobians over P2, and then they have to lie on a K3. And then, so actually, I mean, one of the things I tried to do initially was to generalize his result in a different direction by looking at families of abelian surfaces of different sorts of polarization, right? Polarization 1p. And then in each abelian surface, you don't have a fixed theta divisor anymore. And so it wasn't clear where y is going to come from. So firstly, I realized you could obtain his result using foliation. And then I tried to generalize it in 4 dimensions first. And when that didn't work, I started to look at the higher dimensional cases. And firstly, it's true for n equals 3, true for n equals 4 and 5 if the curves are not hyperelliptic. And these lower genus cases, you can prove them using the sort of relative canonical embedding of the family of curves, and using the fact that these canonical embeddings give you the curves as complete intersections. But then once you get into too high genus, you can't use that argument anymore. But instead, what you have is an argument using foliations, which I'll describe. So it turns out to be true for all n if the degree of delta is at least, or is greater than 4n plus 20, where delta here is the delta in Pn parameterizes the hypersurface parametrizing singular fibers, or singular fibers of X, or singular curves in this family of curves. And the I mean, because the curves are reduced, irreducible, and Gorenstein, you can show that the generic singular curve has a single node. So then the discriminant locus at a generic point should just have you shouldn't have any multiplicity. Okay. So yeah, in case you're wondering, the Brill-Mukai system, the discriminant locus there has degree 6n plus 18. And one can show, furthermore, that the discriminant locus, in this situation at least, has to have degree at least 4n plus 2. So it's sort of not far from the hypothesis that you have this result. So maybe in the last several minutes, I'll just sort of sketch out so how to get this result. So this is the proof of 3. So we let Y be the total space of this family of curves. So this is n plus 1 dimensional, and this embeds in X by the Abel-Jacobi map. Well, here, but without loss of generality, you can assume that you're dealing with degree 1 Jacobians. So then there's a canonical embedding of the family of curves into their Jacobians, and so you get Y as a submanifold of X. And so I mean this is n plus 1 dimensions. This is 2n dimensions. So one can show that because by hypothesis X is smooth, you can show that implies Y has to be smooth as well. And so in this case, you get you don't have to worry about just working on the smooth locus. Y is smooth, but you still have to worry about the characteristic foliation being possibly not regular. So the rank or the foliation could still jump as you move around Y. So, but what you do first is you find you try to find rational curves in here that will be in the leaves of the characteristic foliation. So for generic line L in Pn, consider the surface sitting above L inside this family, and then use classification of surfaces. Is not minimal. So you have rational curves in Z, and you've got -1 curves in there, and so this implies we get lots of rational curves, right? For each generic line in here, above that you have rational curves sitting in Y. So you get rational curves in Y, and with a bit more work, you can show they lie in the leaves of the characteristic foliation. So on the way after you have these after you find these rational curves, you then show in fact that this foliation is regular everywhere on Y. In fact, you end up showing that Y is a coisotropic submanifold of X. So eventually, you show the leaves once you find all these rational curves, you can then characterize the leaves and show the leaves are isomorphic to projective spaces. And the space of leaves is a K3. So this is you're following this general philosophy I described earlier of you're taking some submanifold in Y, quotienting by the space of leaves, quotienting by the leaves to get down to some lower dimensional, in this case the K3 surface, and then finally you can reconstruct everything from the K3 because the curves in this family, which is the same as Y. Y is just a total space of C. These project isomorphically to their image in S. Okay, so in the end, you show that the curves all lie in this K3 surface, which you sort of extracted from the situation we started. So this sort of, I think, illustrates this fantastical idea earlier, that you want to start with some high-dimensional thing and extract from that a K3 or abelian surface that allows you to reconstruct the total space. Obviously, there are some challenges along the way. So it'd be interesting to find other examples where one can get these nice submanifolds that give these nice results in the end. So this is where the hypothesis on the degree comes in. I mean, you look at so this is fibered over P1 by genus n curves. The degree tells you how many nodal curves are in that family, and then you just look at the invariance of the surface and use classification of surfaces to see that can't be a rational surface. I mean, you can also show, in fact, that the 2-form one here has to restrict to a and gives a non-vanishing 2-form one here. So that gives some more information about the surface. On Z? Yeah, 2n minus 2. Well, yeah, that's the answer. Yeah, I mean.
Do you know, like, without knowing it from the text?
I don't think you. I mean, you discover that a posteriori, but you don't. It's not something